Okay, let's relate this back to quantum computing. And we're going to relate it to an important concept, which I'll call, or which is called, measuring in another basis. Okay, measuring in another basis. So suppose your algorithm has some basis, two-dimensional basis like f, perpendicular basis g, like in its mind. Or you might say, or it, knows some angle alpha. It's computed some angle alpha that it finds interesting. Then I want you to consider the following tiny algorithm, which is called measuring or maybe extracting in the FG basis. Okay, this is like a tiny quantum algorithm that takes one qubit A. Step one, we're going to do rotation by negative alpha on qubit A. And this is like the new instruction which I've given you. I let you do any rotation you want now. And then step two, you extract A, or extract all. Let's just imagine we only have one qubit. But, like when you extract A, like normally it outputs or displays like 0 or 1. But we're just going to have it like print something different. So we'll say like, if the display would be 0, then display like the string f instead. And on the other hand, if the display would be 1, then display g instead. Okay, so this is my little two-line function called extract in FG basis. And what does it do on a qubit? It rotates it, and then it prints out either f or g, and then A is like deleted, as usual. Okay, now we might ask, what happens when you do this on a generic qubit? So let's say if the state of A is V, this one that we've been talking about, what is the probability that this prints out F? The final display is F. Okay, it's kind of like this is your qubit. Well, let's think about it. This is your qubit state, V, and then you rotate everything by negative alpha, so like clockwise by 10 degrees. And then you measure, you extract in the sort of usual basis with respect to 0 and 1. Well, we can just figure it out. It's sort of up here on the board. Okay, so after line 1, the state is, the rotation by negative alpha of V. So what is the probability of the display is F? Well, it's kind of the square of the amplitude on 0. It's the square of the 0th coordinate. But we just finished figuring out that like the 0th coordinate is the inner product between ket V and ket F. So the probability that this would output 0, and therefore we change the output to F. So the probability of seeing F is this inner product squared. It's 0 inner product this vector squared, which is F inner product V squared. Or you could say it's like cosine of this gamma squared, where this gamma is the angle between V and F. Okay, so this is just like a new way to like extract or measure a qubit, where you're like, I don't kind of want to know about like how much amplitude is there on 0 and how much amplitude is there on 1. I kind of want to know like how much amplitude is there on F and how much amplitude there is on G. This like different basis. Okay, and it kind of gives you outputs that are like, you 100% get output f if your state vector v is f. You 100% get output g if your state of your qubit is g. And if you're like this v, where you're like mostly in the direction of f and only a little bit in the direction of g, then like you have a high probability of outputting f and a low probability of outputting g. Any questions about this? So we're going to use this like tiny subroutine a lot, even though it's very simple, because like it has like some nice geometric meaning. Okay, now is a good time to talk about this extract operation or this measurement operation. So all along, we've had this command extract or extract all, which, you know, for one qubit, it displays either 0 or 1 on a screen, and then that qubit is like destroyed. Okay, this is what we've had so far. And for some physical implementations of qubits, this makes sense. So if like the qubit is like the spin of an electron, and like the measurement device is like putting it into that Stern-Gerlach tube, and then it either strikes the top screen and makes it glow, or it strikes the bottom screen and makes it glow. After you measure it, like that electron is, I don't know, it's somewhere in the screen, and like you can't do anything with it. This is called a destructive measurement, because after you do it, the qubit is destroyed. And in our pseudocode, this extract stands for a destructive measurement, because like the qubit is deleted after you're done. Now, actually, for some other kinds of physical implementations of measurements, the qubit is not deleted. It's still like physically around. And however, whenever you physically measure this qubit, if it's still like the physical object is still around, its state changes. Its state, quote unquote, collapses. And it collapses or changes to 100% amplitude on whatever the outcome display was. So for some, what I'm saying is for some physical implementations of qubits, there is the physical possibility to do something called the nondestructive measurement. And after you do this, it has the same rules as extract all, except it doesn't delete the qubit. The qubit is still there. But it has like a new state where like all the amplitude, like amplitude 1, is on whatever the measurement outcome was. And you might say to yourself, oh, maybe, you know, I should build my qubits in such a way that this is possible, and then I'll have like a more powerful thing I can do. Instead of this stupid extract, which always deletes my qubit, I can do like a command that corresponds to this, and, you know, I'll still get the measurement outcome, the display, but then I'll still have that qubit, albeit in the new state. Well, don't get too excited, because you can always simulate this yourself if you want with the instructions we already have. So I'm henceforth going to call this like the measure command. But we don't really need it because we can simulate it as follows. So if you want to do measure A, then just extract A. So that deletes it, but it also reports to you back either 0 or 1. And so let's just let A, little a, be the output bit. Okay? This is like a classical bit or Boolean variable. And then you can just look at it, and if it's like, oh, if it's 0, then I'll just make a new qubit in state 0. And if it's 1, I'll just make a new qubit in state 1. So I'll just make a new qubit. That's in state 0. And then I'll be like, oh, if A was true, I'll just toggle it. Okay, so this is code that you can use for non-destructive measurements. And we'll like take this as a black box and just call it a measurement. So this is like code that extracts information and collapses the state, and the qubit sticks around. We can also like do since I have it up here, let's do this. We can therefore also have like measure in the FG basis. We'll do the same thing. We'll rotate by minus alpha and get A. Then we'll extract A. And then we'll say let A be the new displayed outcome. And finally, okay, if this A was 0, which kind of corresponds to like F, then, oops, we should stick a new qubit here. We'll remake A. Then we'll rotate by alpha on A. Else, if A was 1, which corresponds to G, then we'll rotate alpha plus 90 degrees on A. Okay, so once we extracted and learned like whether it corresponded to F or G, with extract, it destroys the qubit, but then we could just remake the qubit in whatever state it was reported to be in. Okay, so I want to show you one more thing before we go. My favorite way to model one qubit, or to think about one qubit, is with photon polarization. Polarization is like the direction the photon is like wiggling. And if you go to the movies and you get like those 3D glasses, they look like this. These lenses are physical devices that implement a semi-destructive measurement. So like this piece of plastic is such a lens. You can buy this for 90 cents. And it's semi-destructive in the sense that like if you hold it like this, when a photon comes in, it's like it measures the photon in the usual way. It extracts it and gets back, the piece of plastic gets back 0 or 1. And if it's 0, which means horizontal, then it lets the photon pass through. And so the photon still exists, and it's in state 0. And if the measurement outcome is 1, which is vertical, it destroys it, or it blocks it, and it gets turned into heat. So this is a cool piece of equipment that you can buy for 90 cents, and it acts halfway between a destructive measurement and a non-destructive measurement. For one measurement outcome, it destroys it, and for one measurement outcome, it doesn't destroy it. And it's really cool. I'll do this next time, but you see, if you take your cell phone, like mine, it has all sorts of photons coming out of it, streaming at your eyes. And due to the way LCD screens work, 100% of the photons coming out are in the state ket plus. They're in the state 45 degrees rotated. Which means if you do measurement in that 45 degrees, which is like this, 100% of them get measured to 45 degrees, and 100% of them pass through. But if you do it in the 90 degrees, or if you do it this way, it 100% of them get blocked, and so only blackness comes through. And then there's one final trick you can do. If you hold it like this, no light is coming through. But then if you put this in, more light is coming through. Which is weird, right? If you didn't know anything about quantum, you'd be like, oh, you've blocked all the light. And now I'm going to put in a further block. But when you do that, more light comes through. So next time I'll tell you, or you can try to figure out, why this happens. It's to do with, the laws of quantum measurement. And you could also think about, why does the cell phone manufacturer manufacture it so that the light coming out is at 45 degrees angle? Why did they do that? Well, you can think about it. I'll tell you next time. Okay, see you on Tuesday.